This research paper addresses the problem of causal discovery in linear non-Gaussian structural equation models with unobserved confounding. The authors propose a recursive algorithm that identifies the causal structure and all possible causal effects from observational data, allowing for latent confounding. The paper builds upon the framework of linear non-Gaussian acyclic models, which are identifiable but challenging to estimate due to the presence of latent variables. The authors denote the observed variables as X and the unobserved variables as L, representing the latent confounders as independent latent factors in a directed acyclic graph. DAG G. The linear non-Gaussian acyclic model is defined by the equation xi equals n array summation j element of pa I lambda I j x j plus n array summation j element of pa I gamma I j l j plus epsilon I, where epsilon j and lj are mutually independent and non-Gaussian. The coefficients lambda ij and gamma ij represent the direct causal effects among observed and latent variables, respectively. The authors discuss related work, including the ICALINGAM method, which estimates the causal structure and effects by rewriting the model as x equals b epsilon and using independent component analysis. However, this approach has limitations, such as convergence to local optima and lack of scale invariance. The authors also mention the direct Lingham method, which recursively identifies a source node and estimates causal effects using regression and independence tests. The proposed algorithm addresses the limitations of existing methods by using rank conditions on matrices formed from higher-order cumulants to identify the source and estimate the causal effects. The algorithm operates recursively, eliminating the influence of the identified source and its latent parents from the data. The authors prove asymptotic correctness under the assumption that the number of latent variables never exceeds the number of observed variables locally. Simulation studies demonstrate that the proposed method achieves comparable performance to overcomplete ICA, even without knowing the number of latent variables in advance. The authors highlight the significance of their approach in addressing the challenges of causal discovery in the presence of latent confounding. Key equations and concepts include the linear non-Gaussian acyclic model, the path matrix B, and the rank conditions on matrices formed from higher-order cumulants. The authors also discuss the limitations of existing methods, such as convergence to local optima and lack of scale invariance. The flow of ideas connects the introduction of the problem and related work to the proposed algorithm and its theoretical guarantees. The authors highlight the significance of their approach in addressing the challenges of causal discovery in the presence of latent confounding. Causal discovery with unobserved confounding is a challenging problem, prone to optimization and statistical errors. Existing methods, such as direct Lingam, Ivlingham, Parselingham, RCD, and Bang, rely on independence tests of residuals to address this issue. However, these methods have limitations, such as requiring specific graph structures or not allowing for nonlinear confounding. A recent approach by Kai et al. 2023 uses conditions involving cumulants to find structures of the form xi left pointing arrow L right pointing arrow xj or xi right pointing arrow xj, estimate coefficients, and remove the effect of the latent. However, this method requires assumptions about the true graph, including that each latent has at least 3 observed children. This paper proposes a novel approach that extends existing methods and proves conditions for finding a source in a completely arbitrary directed acyclic graph, DAG. Once a source is found, its effects on its descendants are estimated using polynomial equations for the edge weights. The method then removes the effect of the source from the data and continues until the entire structure is discovered. This approach finds the whole structure whenever locally the number of observed nodes is higher than the number of latents. The paper also introduces notation and provides background on linear structural equation models with latent variables and higher-order cumulant tensors. It restricts itself to the case where each latent has no parents and at least 2 children, as this does not affect the observed distribution or total causal effects among observed variables. The linear structural equation model M, G, for the graph G is defined as the set of all joint distributions Px of observed random vectors x solving the structural equations. The paper assumes that all moments of the error terms and latents are finite and that the random vectors are centered. It also assumes that all non-zero coefficients and cumulants are generic, meaning that the results hold for Lebesgue almost every choice of coefficients and cumulants. The paper provides a formula for the number of choices for edge weights that lead to the same observed distribution and discusses the implications of this result. Causal discovery with unobserved confounding. The paper discusses the issue of unobserved confounding in causal discovery, which is a significant challenge in identifying causal relationships between variables. It introduces a new approach that leverages the concept of path matrices to represent the causal effects from exogenous sources to observed variables. The path matrix B encodes the total causal effects from each exogenous source to every observed variable, and it is in one-to-one correspondence with the pair, lambda, gamma. The paper also highlights the non-identifiability of the causal order and the number of latents, as demonstrated by an example graph with two possible choices for B, resulting in different causal structures. The paper further explores the relationship between the number of choices for lambda, gamma, and the graph structure G. It is shown that the number of choices, denoted as I, is determined by the number of observed nodes and their relationships with latents and other observed nodes. A lemma is presented, which states that if Px is defined via generic coefficients, then G is the unique minimal graph such that Px element of Mg, and the number of choices for lambda, gamma, compatible with Px and G is given by I, sparse. This result is proven in the appendix and provides insight into the additional edges introduced by swapping columns in the path matrix. Moreover, the paper addresses the question of when the edge weights are uniquely identifiable, a topic also explored in Adams et al., 2021. The authors derive necessary conditions for the unique identifiability of the edge weights, shedding light on the complexity of causal discovery in the presence of unobserved confounding. In the context of causal discovery with unobserved confounding, this research focuses on the linear structural equation model M2, L for the graph G2, L, which encompasses all possible graphs for two observed variables. The model assumes that each latent has at least two children, and it allows the edge weight lambda 21 to be 0. There are L+1 compatible path matrices for this graph, with the other L options arising from swapping O1 and Lj for some j element of L. If lambda 21 equals 0, then ing2, L, sparse coincides with ing2, L. Otherwise, ing2, L, sparse equals 1. To infer the number of latent variables and the causal order, a matrix formed from cumulants is utilized. For instance, if there are no latents, two matrices A, 2, 3, 1 right pointing arrow 2 and A, 2, 3, 2 right pointing arrow 1 are defined. If 1 is the source, A, 2, 3, 1 right pointing arrow 2 has rank 1, and if 2 is the source, A, 2, 3, 2 right pointing arrow 1 has rank 1. Similarly, for L equals 1, matrices A, 3, 4, 1 right pointing arrow 2 and A, 3, 4, 2 right pointing arrow 1 are introduced. A, 3, 4, 1 right pointing arrow 2 has rank 2 if 1 is the source, and A, 3, 4, 2 right pointing arrow 1 has rank 1 if 2 is the source. To extend to an arbitrary number of latents, the concept of symmetric flattening is introduced. For H is less than or equal to K, the HTH flattening of the symmetric tensor T element of SymK is a matrix with rows and columns indexed by subsets of M in entries given by the cumulant T1, IK. This method provides a foundation for the algorithm for an arbitrary number of variables. Here is a combined summary of the two pages. The authors present a method for causal discovery with unobserved confounding, focusing on the construction of a matrix A, K1, K2, 1 right pointing arrow 2 that facilitates the identification of the number of latents and the estimation of causal effects. The matrix is constructed by stacking the K1th symmetric flattenings of covariance matrices C, K1, C, K2, vertically and removing the last column. The authors prove that the rank of this matrix is at most L+1, where L is the number of latents, and generically exactly rank min, L+1, M, where M is the minimum of the number of rows and columns of the matrix. To obtain a non-trivial rank bound, The authors choose the smallest possible orders K1 and K2 such that L plus 1 less than 1 plus 2 plus K2 K1 plus 1. This choice of orders yields a quadratic polynomial, and the authors show that K2 K1 needs to be greater than or equal to the maximal root of this polynomial. Once the source and the number of latents are inferred, the authors estimate the causal effects by extending the matrix A, L, 1 right pointing arrow 2 with an additional row containing the entries B21, BL plus 2 21. This extension does not increase the rank of the matrix, and the minors of the extended matrix provide polynomial equations for B21. The authors prove that the roots of these polynomials give the L plus 1 possible values for B21. The authors illustrate their method with an example, showing that the extended matrix A, L, 1 right pointing arrow 2 has a rank of at most L plus 1 and that each minor of size L plus 2 vanishes. They also show that the minors of size L plus 2 provide polynomial equations for B21, which can be solved to estimate the causal effects. Overall, the authors present a novel method for causal discovery with unobserved confounding, which relies on the construction of a matrix A, K1, K2, 1 right pointing arrow 2 and the estimation of causal effects using polynomial equations derived from the minors of this matrix. Here is a combined summary of the 2 pages. The authors present a method for causal discovery with unobserved confounding, leveraging the concept of linear structural equation models. Lemma 5 establishes that under the model M2, L, a specific equation system is generically uniquely solvable if K is greater than or equal to L plus 1. This result enables the estimation of causal effects within an arbitrarily large graph. The authors aim to identify one valid choice for the matrix B, which represents the causal relationships between variables. They focus on finding a source node and its effects on other nodes, using an iterative procedure. Lemma 6 provides a crucial result, stating that the marginal distribution of every pair of observed nodes satisfies a linear structural equation model. This lemma enables the identification of the ancestor node in a pair of nodes by sequentially testing the rank of the matrix A, L. The authors then present a criterion for identifying a source node, which is a node that has no ancestors. Lemma 7 states that a node S is a source if and only if for all other nodes W, the minimum value of L such that the rank of A, L, S right pointing arrow W is L plus 1 is less than or equal to the minimum value of L such that the rank of A, L, W right pointing arrow S is L plus 1. The authors then discuss how to combine the pairwise pictures of causal relationships to form an overall graph. They propose examining the cumulants in the marginal models to differentiate between possible graphs. By aligning the cumulants, they can associate latent variables with their descendants. Finally, the authors note that the causal effects in the marginal models coincide with those in the overarching model, enabling them to fill in all columns of the matrix B corresponding to the source and its latent parents. They enumerate the latents arbitrarily, fixing the arrangement of the corresponding columns in B. Key terms and concepts include linear structural equation models, causal discovery, unobserved confounding, and the matrix B representing causal relationships between variables. The authors use technical terms such as marginal distribution, rank of a matrix, and cumulants to describe their methodology. The results are presented in a formal and precise manner, with equations and lemmas used to establish the key findings. In the context of causal discovery with unobserved confounding, the paper discusses the next iteration in the algorithm for identifying the source node in a directed acyclic graph, DAG. The authors introduce a new variable x, 1, w, which is a function of observed variables xw and latent variables L1, Lm. This new variable is essential for the next iteration of the algorithm, as it allows for the estimation of the cumulants of the exogenous sources. The paper also presents a practical implementation of the proposed algorithm, outlining the steps involved in estimating cumulants, identifying the source node, and adjusting the threshold for the rank test. The authors provide a detailed explanation of how to compute the singular values of A, L, V right pointing arrow W and determine if the rank condition from Theorem 3 is satisfied. They also discuss the importance of ensuring scale-freeness in the rank test and provide a link to their code repository for further reference. The paper includes an example illustrating the necessity of the assumption in Lemma 9, which highlights the importance of having distinct observed nodes as children of the latent parents of the source node. This example demonstrates how the linear equation system for second-order cumulants can become invertible under certain conditions, allowing for the estimation of the cumulants of the exogenous sources. Overall, the paper presents a comprehensive approach to causal discovery with unobserved confounding, providing theoretical foundations and practical guidelines for researchers working in this area. The proposed algorithm and its implementation are designed to handle complex scenarios involving latent variables and unobserved confounding, making it a valuable contribution to the field of causal inference. The paper presents a novel algorithm, RELVLINGAM, for causal discovery in the presence of unobserved confounding variables. This algorithm leverages the concept of linear non-Gaussian acyclic models, LINGAM, to identify causal relationships between observed variables. The approach is based on the estimation of cumulants, which are statistical measures that describe the shape of a probability distribution. The algorithm iteratively identifies the source variable in the system, estimates the causal effects, and aligns the latent variables by aligning their cumulants. It also adjusts the bound on pairwise confounding in each iteration using information from previous iterations. The paper also discusses the theoretical guarantees of the algorithm, including the condition for the algorithm to return the true path matrices compatible with the probability distribution Px. This condition is related to the rank of certain matrices derived from the path matrix and the number of latent variables. The algorithm can recognize when this condition is not fulfilled, indicating an underdetermined linear equation system for estimating cumulants. In addition to the theoretical analysis, the paper includes simulation studies comparing the performance of RELVLINGAM with the RECA method proposed in Salakalibar et al., 2020. RECA is used as an idealized benchmark, leveraging overcomplete independent component analysis to compute a path matrix that results in exogenous sources close to having independent components and far from being Gaussian. The simulation setup highlights the advantages of RELVLINGAM over RECA, particularly in terms of identifying the correct number of latent variables and avoiding cyclic graphs. Causal discovery with unobserved confounding, a comparative study of RELVLINGAM and RECA. The authors investigate the performance of two causal discovery algorithms, RELVLINGAM and RECA, in the presence of unobserved confounding. They conduct simulations using 6 different graph structures, varying the noise distribution and sample size. The results show that RELVLINGAM exhibits higher precision, while RECA outperforms in terms of recall. The authors first evaluate the impact of varying the noise distribution on the results, finding that it has little effect. They then focus on gamma-distributed noise and perform 1,000 replications for each setting. To address the non-uniqueness of the true causal matrix B, they use a convention of setting the edge from a latent to its oldest child to 1. However, since RECA does not necessarily return an acyclic graph, they follow an alternative approach suggested by Salakalibar et al., 2020. The results show that RECA tends to excel in terms of RMSE, particularly for low sample sizes. However, its performance does not improve notably with higher sample sizes. In contrast, RELVLINGAM's performance improves with increasing sample size. The authors attribute this difference to the algorithm architectures. RELVLINGAM first estimates the graph structure and then infers the edge weights, while RECA searches directly for the best-fitting path matrix. The authors also investigate the effect of specifying the overall number of latents L for RECA and the upper bound on pairwise confounding Lmax for RELVLINGAM. They consider 2 options for Lmax: the actual highest number of pairwise confounding within the graph, and this value increased by 1. The results show that RELVLINGAM's performance improves with increasing Lmax. The simulation results are presented in figures 7 and 8, which show the RMSE, recall, and precision of both algorithms for different settings and sample sizes. The results highlight the strengths and weaknesses of each algorithm and provide insights into their performance in the presence of unobserved confounding. Causal discovery with unobserved confounding, a novel approach. The proposed method, RELVLINGAM, demonstrates state-of-the-art estimation accuracy in identifying the graph structure of a linear non-Gaussian structural equation model featuring latent confounding. This is achieved by leveraging cumulants of the observed distribution, which enables the unique identification of the graph structure. The method iteratively identifies a source node of a causal diagram and infers the number of its latent parents using a rank constraint on a matrix formed from cumulants. Polynomial equations are then used to estimate the source's causal effects on its descendants. The algorithm is shown to accurately identify the number of latent variables, even when the upper bound on pairwise confounding is not tightly set, which represents a significant advantage over existing OICA approaches. Additionally, the method relaxes the assumptions required by the true graph, only requiring that the locally number of latent variables is lower than the number of observed variables. The identifying equations derived can also be used to estimate specific causal effects when the graph is already known. Furthermore, the iterative nature of the method could be exploited to incorporate prior knowledge. Future research directions include developing extensions of the algorithm that can accommodate sparse, high-dimensional settings. Appendix A provides the proofs of Lemma 1, Theorem 3, and Lemma 6. Specifically, the proof of Lemma 1 shows that every other compatible path matrix B can be obtained by swapping columns in the original path matrix B. The coefficients for the observed variables corresponding to B form the matrix lambda, which can be calculated using the permutation matrix S. The sparsity patterns of lambda, gamma, and lambda, gamma are compared, and it is shown that the graph G, encoding the sparsity pattern of lambda and gamma, cannot contain fewer edges than G, making G the unique minimal graph. The mathematical derivations and proofs presented in the appendix provide a rigorous foundation for the proposed method, demonstrating its theoretical soundness and potential for practical applications in causal discovery and estimation. In the context of causal discovery with unobserved confounding, the paper discusses the concept of a graph G that incorporates edges v right pointing arrow I for I element of P, V, whenever there is an edge W right pointing arrow I in the original graph, and edges J right pointing arrow I for I element of P, V, J element of P plus L, W, whenever there is an edge J right pointing arrow V and W right pointing arrow I in the original graph. This is to avoid introducing new edges. The paper also presents a formula for in, sparse, which is derived from the conditions mentioned above. The paper then proceeds to prove Theorem 3, which involves the use of a lemma that states that the set W equals W. Y equals Wx for some x element of x, 0, y element of y, 0, has Lebesgue measure 0. This lemma is proven by parameterizing W using a lower dimensional subspace of RL plus 1, and then showing that each component of W has measure 0 using Sard's theorem. The proof of Theorem 3a involves the matrix A, K1, K2, 1 right pointing arrow 2, which consists of cumulants C, K, I1, Ik where at least one of the indices I1, Ik equals 1. Using lemma 2, these cumulants are expressed as a sum of cumulants involving epsilon and L. The paper then simplifies this expression to obtain cum, K, epsilon 1, B, Ij equals 2, 21 plus L, summation display J equals 1 cum, K, Lj, B, Ij equals 2, 2, J plus 2. This result is crucial for the overall argument of the paper, as it helps establish the relationship between the observed variables and the latent variables in the context of causal discovery. Causal discovery with unobserved confounding. The authors present a novel approach to causal discovery in the presence of unobserved confounding variables. They introduce a matrix A, K1, K2, that represents the causal relationships between variables, and show that its rank is at most L plus 1, where L is the number of confounding variables. The authors then prove that the rank of A, K1, K2, is precisely min, L plus 1, M, where M is the number of variables. The proof involves showing that the first L plus 1 rows of the matrix M are linearly independent. The authors use a proof by induction, assuming that the set W0BO union Wj-1 Bj-1 is linearly independent, and then showing that the sum yj-1 plus wjxa is direct. They employ lemma 11 to verify the assumption B, for yj-1, and then show that the sum is direct for generic wj. The authors also prove lemma 6, which states that the set of blocked ancestors of a variable w given V is a disjoint union of two sets. They use this lemma to show that the joint distribution of xv and xw can be written as a sum of terms, each of which depends only on the ancestors of V and W. The proof of lemma 6 involves showing that the joint distribution of xv and xw can be written as a sum of terms, each of which depends only on the ancestors of V and W. The authors use the shorthand an, V, W, for an, V, intersection an, W, and denote the set of blocked ancestors of W given versus as BLV, W. They then show that the joint distribution of xv and xw can be written as a sum of terms, each of which depends only on the ancestors of V and W. The author's approach has significant implications for causal discovery in the presence of unobserved confounding variables. Their results provide a new framework for understanding the relationships between variables in complex systems, and have the potential to improve our ability to identify causal relationships in a wide range of applications. Equations and algorithms. The authors use a number of equations and algorithms to prove their results. These include the definition of the matrix A, K1, K2, the proof of the rank of A, K1, K2, and the proof of lemma 6. The authors also use a proof by induction to show that the sum yj-1 plus wjxa is direct. Figures and tables. There are no figures or tables in the provided text. Limitations and future work. The authors do not discuss any limitations or future work in the provided text. However, it is likely that the authors will discuss these topics in the full paper. Assumptions. The authors assume that the confounding variables are unobserved, and that the causal relationships between variables can be represented by a matrix A, K1, K2. They also assume that the rank of A, K1, K2, is precisely min, L plus 1, M. Technical terms. The authors use a number of technical terms, including causal discovery, unobserved confounding variables, matrix A, K1, K2, rank of A, K1, K2, linearly independent, proof by induction, and lemma 11. In the context of causal discovery, the presence of unobserved confounding variables can significantly impact the accuracy of inferred causal relationships. This paper addresses this challenge by proposing a novel approach that leverages non-Gaussianity in the data to identify causal structures even when latent confounders are present. The method is based on the linear non-Gaussian acyclic model, LINGAM, which has been widely used for causal discovery in various domains. The proposed approach utilizes higher-order cumulants to detect the direction of causal influence between variables. These cumulants are statistical measures that capture non-Gaussian features of the data distribution, allowing for the identification of causal relationships even in the presence of latent confounders. The authors demonstrate how their method can be applied to both observational and interventional data, providing a comprehensive framework for causal discovery under non-Gaussianity. The paper also discusses the limitations of existing methods, such as the need for strong assumptions about the underlying causal structure or the requirement of multiple interventions. In contrast, the proposed approach does not require any prior knowledge of the causal graph and can handle both direct and indirect causal effects. Furthermore, it is shown to be robust against various types of confounding, including unobserved confounders. The authors provide a detailed analysis of the theoretical properties of their method, including consistency and asymptotic normality. They also present simulation studies that demonstrate the effectiveness of their approach in identifying causal relationships in the presence of latent confounders. These results highlight the potential of this method for real-world applications where unobserved confounding is common. In conclusion, this paper presents a significant advancement in causal discovery by leveraging non-Gaussianity to handle unobserved confounding. The proposed approach offers a promising solution for researchers seeking to uncover causal relationships in complex systems, particularly those involving latent variables.